Hello. So, in all these sessions, earlier sessions, we have been talking about the gyroscopic couple, right? So, in today's session, we will talk about the effect of gyroscopic couple on two-wheelers. Now, most of us have been experiencing riding a two-wheeler, right? We have as well seen how the stability of a four-wheeler is getting influenced due to this effect of gyroscopic couple. But in case of two-wheelers, this is somewhat different. Different in a way, if I compare the turning condition of a four-wheeler and a two-wheeler, you will see that if I assume this as the shaft of the wheel of a four-wheeler, when a four-wheeler is taking turn, in that case you will see that the spin axis is absolutely turning in the horizontal plane, right? But there is a little bit difference in case of a two-wheeler. Now, when we are riding a two-wheeler in a straight path, the vehicle and the rider is upright. But during the turn, you will see that the rider and the vehicle, they are getting tilted. Now, if I compare with the vertical, so it is tilting while taking a turn. So, why is it so? This is to compensate, right? So, compensation of what? Because when vehicle or a two-wheeler is turning, so of course during the turn there will be an overturning couple which will be acting on that entire system. So to provide that compensation, the rider is tilting the vehicle. So if now I compare the wheel condition of a four-wheeler and a two-wheeler, there will be a little bit of difference. Now when say this is for a four-wheeler and this is for a two-wheeler. Now during a turn, let us say a right turn, when a four-wheeler is taking a right turn, the axis of spin is turning about, simply the motion of the axis of spin is on the exit plane or the horizontal plane, whereas in case of a two-wheeler, what is happening, the axis of spin is getting tilted and then it is turning, or then it is turning in the exit plane. So this is what is a major difference. So technically that is how we can then try to understand how the magnitude of gyroscopic couple is getting affected due to this condition. So let us try to understand this in this session, right? So I'll take the condition, say this is the right. So this is the wheel at the upright condition, right? And likewise I can finish this diagram. So let's say this is the condition. So as I am showing here, now this is the front view you are seeing and this is the top view. So in top view I can see the two wheels, the front wheel and the, so I'll take this one as the front wheel and this as the rear wheel, and this is the engine, and the two-wheeler is moving in the forward direction, right? And so this is the axis of rotation, so when it is moving forward, so and this is the axis of rotation of the front wheel, this is the axis of rotation of the rear wheel, and here we have considered the engine axis. So this is the engine, so the engine and the rotating parts, whatever transmission taken together, equivalent if I say, is considered to be parallel to these two spin axes. So the engine axis as well as the wheel axis, they are parallel to each other, right? So this is the upright condition when the vehicle is moving in the straight path. Now when the vehicle is taking a turn, the two-wheeler is taking turn, so in that case then what is happening? The wheels are getting tilted and the rider is taking the turn. So both the front wheel and the rear wheel, they are getting tilted, and that is how the turn is taking place as well. You will see this in this case. The engine axis is also getting tilted. Now let us say during taking a turn, again I will consider the turn to be, let us say the vehicle is taking a right turn. Right? Again, the turn is taking place on the ground or the exit plane. So I have to take a judgment from the top view. So when I am looking from the top view, the vehicle is taking a right turn. So again, the axis of precision in this case will be the vertical y-axis. Right? So now when it is taking a turn, let us say now at the upright condition, assuming that this height is lying at the center of the height of the wheels, right? So I am denoting that by H, where H, let us say the CG is at the center, and this is the height of the center of mass or center of gravity, what we call. So that is at height H. And when it is taking a turn, let us say it has tilted, the vehicle or the wheel or the spin axis is tilted by theta angle from the vertical, right? So now we'll try to understand how basically this gyroscopic couple is affecting during the turn of the vehicle. So for that, first we'll try to find out or understand the magnitude of these this gyroscopic couple. So first I'll have to find out the gyroscopic couple will be one, definitely due to the wheels, right? How many wheels? So it is a two-wheeler, so there will be two wheels, and second, the engine and rotating parts. Gyroscopic couple due to the engine and the rotating parts. That means the total gyroscopic couple will be the gyroscopic couple due to the wheels, right, and plus the gyroscopic couple due to the engine, right? Now it has to be, as total couple will be plus minus these two couples. Again, when the sense of rotation of the spin axis and the spin axis of the engine, when they are same, there will be the addition of these two couples. If the engine is rotating opposite to the spin axis but it is parallel, then in that case it will be negative, right? So here I consider both engine and wheels, they are moving in the same sense, so I will take this as the total addition of these two couples as the total gyroscopic couple. Now we know that the magnitude of gyroscopic couple, let us say for the wheels, it will be I omega P, where omega is the omega of spin, omega of the wheel, and I is the mass moment of inertia of the wheels, and omega P is the precision velocity, right? Now here we will have to understand how the magnitude is getting affected. Now when the turn is taking place, we need to, the wheel is tilted with respect to the vertical by this angle theta, right? So the condition of the spin axis, is this. So I'll just show the axis. So the spin axis is this, right? Now, what is I omega? I omega is the angular momentum, right? The I omega is the angular momentum of the wheel, and this is a vector. And how I will specify the direction of this vector? Definitely the direction of the vector is always perpendicular to the plane of rotation. Now let us understand here what is happening. The wheel has tilted this way. That means the plane of rotation of the wheel is tilted. So the vector direction will be perpendicular to the rotation. So depending on whether it is clockwise or counterclockwise, the vector will be perpendicular to. So let us say the vector is pointed in this fashion. Or if I say in our case, when this is turning clockwise, so if I take the right hand, if I consider the right hand rule, in that case the vector of I omega will be pointing outwards, so it will be in this fashion, in this direction. This will be I omega, right? But what is happening in this tilting condition? The vehicle is taking the turn, right? So the magnitude of couple is affected. See, magnitude of couple is what? It is the rate of change of angular momentum. We have seen in the expression which we derived earlier, and that is how we are getting this. But here then what is happening? So the rotation of the spin axis is taking place in an absolute horizontal plane, but the axis is tilted, right? So this vector is I omega, so which this component of the, so this horizontal component of this vector will be actually affecting or constituting the magnitude of gyroscopic couple. So if this has, the wheel has tilted by theta, that means this vector has turned by theta, that means this angle comes out to be theta. So in that case I will say this component is I omega cos theta, right? So this I omega cos theta which is turning, this component which is turning, this is constituting the or affecting the magnitude of gyroscopic couple due to the wheels, as well as in case of the engines as well. So both in these cases the component of the horizontal component, that is this component, is going to affect into the magnitude, right? So how my expression is given? So gyroscopic couple due to the wheels will be I omega cos theta, and there are two wheels, right? I omega cos theta to omega p. Again, what is omega p? So this is for, so I give the suffix as VW. So this is for wheels, and similarly for gyroscopic couple due to the engine will be I of the engine, omega of the engine, and the component of cos component of this into omega p. So what is omega p? Omega p is the precision velocity, where I can say omega p is equal to v by r, where this v is the linear velocity of the two-wheeler and r is the radius of turn. So we have considered here the right turn, so it is the radius of turn. So we as well have seen this as so what will be the total gyroscopic couple? So the total gyroscopic couple will be, so I am consider these to be same, so in that case it becomes twice of I of wheel, omega of wheel, right, plus, sorry, twice of I of wheel, E omega E. I can take this cos theta, so cos theta into omega t. So this I get as the magnitude of gyroscopic couple due to the wheels and the engine, right? So this is the magnitude of gyroscopic couple. So now again we will have to understand how this gyroscopic couple is, as only telling the magnitude will not do, as well I will have to make judgment, take the judgment of the sense of this couple, right? So for getting the sense of this couple, so again so this is the y-axis, the two-wheeler is taking a right turn, so the precision looking from the top, if I see y-axis is the precision axis, x-axis is the spin axis, and the z-axis is the couple axis. So x-axis is the spin, y is precision, and z is the gyro couple. So active, reactive, that will decide them. So the spin axis, again when it is taking a right turn, as an observer I will be standing at the center of the turn and making the judgment. So if when I am standing at the center and vehicle is moving forward, that means the wheels are turning clockwise from the point of view of the observer, so the vector will be pointed outwards. So this will be the, so this is the pole, so this is the, so this is the spin vector, so which is turning clockwise. Precision, again vehicle is taking a right turn, so right turn means again it is clockwise, so looking from the top, this vector is pointed downwards, so again it is clockwise. How do we get the how we decide the gyroscopic couple vector? We turn the spin vector in the sense of precision, by 90 degrees. So if I turn it this way, so that means this is the active gyroscopic, this is the active gyroscopic couple. So as an observer, when I am standing behind the two-wheeler and looking at the system, then this vector is pointed outwards, that means this sense of rotation is clockwise. And the reactive couple, so this is active gyroscopic couple, so reactive gyroscopic couple will be exactly opposite to it. So this is the reactive gyroscopic couple, and this vector is pointed towards the observer, so this will be counterclockwise. Now here let us try to understand, in case of a two-wheeler I am not getting any pivotal point as such as in case of a four-wheeler you have seen, where we are getting a ground reaction for that couple, whereas in this case it is the one of the point itself is becoming the pivotal point for the overturning couple. So that means what is happening is the active couple, that means the shaft of the wheel is trying to turn clockwise, right? But the entire frame of the two-wheeler is just trying to turn in the counterclockwise direction. So here if you see, the active gyroscopic couple is in the clockwise sense, right? And the reactive gyroscopic couple, so this is the reactive gyroscopic couple, it is acting counterclockwise. So it is adding into the overturning couple, right? So this is the reactive gyro couple, gyroscopic couple, which is acting outward, right? So this is what is getting added into the system when this two-wheeler is taking a right turn. What is the other thing which is getting included during turn? It is the centrifugal couple. The couple due to the centrifugal force. So when the body is or the vehicle is taking a turn, so obviously a centrifugal force will be acting on the body. So the second factor which is coming into the picture, so first was, so we have seen the first as the total gyroscopic couple, which came out to be twice I of wheel, omega of wheel, plus I of engine, omega of engine, into omega p, and cos theta was common for that. So this was the magnitude of total gyroscopic couple. This is in Newton meters. This is the first thing. And the second, which we are trying to find out now, is due to centrifugal force, right? So what is the force? Centrifugal force is mv square by r. This is the centrifugal force, which will be, now this force will be with newtons. This magnitude of force will be acting through the center of mass. Now this point CG which I have shown is the center of mass. Now during the turn, what is happening? The vehicle is getting tilted. That means the center of mass has taken this position during the turn, and during the turn this centrifugal force will be acting from the center of mass, and that will be acting radially outward. So this theta, I mentioned it here. So this is theta, right? So the centrifugal force will be acting radially outward. So this is the centrifugal force which will be acting radially outward, and this force will be giving a moment, right? So couple or a moment due to this centrifugal force, the magnitude of this couple due to centrifugal force will be this force, right? This force into the shortest vertical height into, now if I see, so we have said that this is height h which is getting tilted. So this is h, right? So if we see this, so we need to find out this distance. So if this is theta, this is theta, this is the hypotenuse side, that means this is, so this is also theta, so this is hypotenuse side, so this is h cos theta. So the centrifugal couple, magnitude of centrifugal couple will be this into this force into h cos theta Newton meter. So we get this as m v square by r into h cos theta Newton meter. And this couple, due to the centrifugal force, this is also acting radially outward. So this is the couple due to centrifugal force. So you can see both these forces, they are acting radially into the outward direction. So now I can say, so the couple due to centrifugal force, this has come out to be, so couple due to centrifugal force is mv square by r h cos theta Newton meter. This will be the magnitude of this, and both these couples, they are acting outward, right? So what will be the magnitude, total magnitude of, so you'll see, so the total overturning couple, this is equal to, comes out to be this twice plus, right, into omega p cos theta plus mv square by r h cos theta. So if I simplify this, so it will be twice plus omega p plus mv square by r to h to cos theta. So this is, I can say, the total overturning couple. I can give you total overturning couple. This comes out to be this. Now, when the vehicle is taking turn, the total overturning magnitude of overturning couple acting on the system is this, right? Now to take a stable means, that means comfortably we are taking the turn. So if I want to have a stable, or if I want to achieve a stable turn, that means this much magnitude of overturning couple has to be compensated by a couple or a moment exactly opposite to it, right? Now that compensation is provided by the rider. That means with the help of the weight of the vehicle and the own weight of the rider, with the help of which this moment, a counter moment to the overturning moment or overturning couple, is to be provided, and that is provided with the help of the weight. So that means from the CG, so this weight is to, we are compensating it with the help of this weight, which is equal to this, right? So this compensation is provided by, and what will be the magnitude of this couple? So this weight is to act at this distance. So we have seen for this triangle, this was h cos theta, so that means this distance, comes out to be H sine theta. So that means this total overturning couple is getting compensated with the help of mg into H sine theta, or I can say this is mgh sine theta, right? So now I can equate this value with this equation. So say when we equate, so we are equating, so when these two magnitudes are equal, then the condition will be stable. So when this is equal to mgh sine theta. So now if I take this to common, so sine theta, so if I say sine theta upon cos theta, sine theta upon cos theta will be this. So twice of plus into omega p plus mv square by r into h, right, divided by mgh, or I can say this tan theta is equal to this numerator bracket divided by mgh. So what is this theta? Now this theta is called as the angle of heel. This theta is called as angle of heel. So now this angle of heel, as the speed of the two-wheeler is increased, the angle of heel will also increase, because this magnitude will increase as the speed is increasing, the wheel linear velocity will be increasing, so omega will be increasing in this case, right? So you will see that this angle of heel also will go on increasing. So that is how the stability of a two-wheeler is getting affected due to this gyroscopic couple. So earlier we have been thinking that it is only the centrifugal force which might be influencing the angle of heel, by which we are again thinking of banking of roads and all, right? But here, when we have understood the gyroscopic effect, we see that due to the speed also, there is an additional overturning couple which is getting introduced into the system, which is not only the centrifugal force. Now this also gives us a scope into thinking. So now if I am thinking for a given road condition, I cannot change the road condition, but now if I want to increase the limiting speed of the condition, I can quote an example, or rather all of us must have experienced or have noticed, if you compare the tires of the earlier two-wheelers. So if I try to show the cross section, say this is the cross section of a tire. So if you just try to remember the cross section of the tires of the olden two-wheelers or the bikes, you'll see that these are somewhat like this, right? So here is the tread. This is the tread portion of the tire. But so in these conditions, if I am increasing the speed, so what is happening? The angle of heel is also increasing for the compensation, because I will be requiring more moment due to the weight. So I am increasing that length, because weight I cannot change. Whatever weight of the rider and the vehicle is there, that has to be constant. What I can manipulate is the radial distance. So as much as I increase the angle of heel in the earlier vehicles, so the tires, cross section of the tires were like this, and they were low speed as compared to the vehicles which are now we are riding. So if you compare it with the say the cross section of tires of nowadays vehicles, if you see, they are like this, if I am not wrong. So you see, so even if I am tilting, so I am getting a scope of providing the friction to maintain the road contact, right? So this angle of the concept of these things are even giving me a scope into modification of the other things which are associated with the vehicle dynamics. So in this session, that is what we have seen today, how the gyroscopic couple is affecting into the stability condition, or how I can say how it is increasing, adding on into the overturning couple, which maybe earlier we were not giving a thought. So as well as these are as well producing what you can say, these are as well adding on additional burden on the bearings at the wheel shaft. So these are definitely need to be taken care of. So that is what we have seen, and how this angle of heel is proportional to, or it is getting affected with the speed of the vehicle, and how we can maybe have scope of like this, as I have quoted example of say the tire. So how they are giving me a scope of thinking of modification of various things which are associated with the vehicle. So that's all for this session, and take care.